Hello students, welcome to today's lecture on theory of machines. In previous lecture, we discussed about the simple band brake. We derived the equation for the force applied in both the conditions of the rotation of the drum, that is clockwise and anti-clockwise rotation of the drum. We also solved a numerical problem based on simple band brake. In simple band brake, one of the end of the band is always connected to the fulcrum point. Simple band brake can neither have self-energizing properties nor it can be self-locked. Now, in today's lecture, we will be discussing about the differential band brakes. We will derive the equations for the force applied in various configurations and also try to find out whether the differential band brake can be self-locking or not. So let's move ahead with differential band brake. Let's see the differential band brake. This is the drum and this is the lever, which has been hinged at this point O, and you can see that the fulcrum is provided somewhere along the length of the lever and not on one side of the lever. This is the shape of the lever. This is the band. One end of the band is connected to this point and another end is connected to this point. The radius of the drum is R and the angle of wrap is theta. The distance of end A of the band from the fulcrum is A and distance of end B from the fulcrum is B. This is the force P that will be applied at the end of the lever, and the distance of force P from the fulcrum is L. So, as the drum is rotating in the clockwise direction, so this will be the tight side and this will be the slack side. The tight side is having tension T1 and slack side is having tension T2. So T1 is the tension on the tight side of the band, T2 is the tension on the slack side of the band, theta is the angle of wrap or contact of the band on the drum, mu is the breaking line friction coefficient, R is the radius of the drum, and P is the force applied at the end of the lever. Now, as discussed earlier, the limiting ratio of tensions is given by T1 by T2 is equal to e to the power of mu theta, and the breaking torque on the drum is given by Tb is equal to T1 minus T2 into R. These two equations we will be using for solving the numericals. Now, in the differential band brake, the band is not connected to the fulcrum, as in case of simple band brake. So the effectiveness of the force P depends upon the following: the direction of rotation of the drum, the ratio of the lengths A and B, and the direction of applied force P. So depending on the configuration of this differential band brake, the force P will be applied either from upward to downward or from downward to upward, depending on the length of A and B. This we will see in the upcoming discussion. Now, to apply the brake on the rotating drum, the band on the drum should be tightened. And this is possible if A is greater than B and the force is applied from the... This is possible if force P is applied in the downward direction when A is greater than B, and force P is applied in the upward direction when A is less than B or B is greater than A. These configurations we will discuss one by one. So let's start with the first case. The first case is when A is greater than B and P is applied in the downward direction. You can see in the diagram that the distance A is greater than B and the force is applied in the downward direction. When the force is applied in the downward direction, this side of the belt will be pulled up and the band will be tightened. When the force is applied in the downward direction, this side of the band will be pulled up and the band will be tightened and the brakes will be applied. If the force is applied in the upward direction, in this case suppose, then in that case this portion of the lever will come down and the band will be loosened and thus the brakes will not be applied. So if A is greater than B, then the force should be applied in the downward direction. Now let's see the counterclockwise rotation in this case and let's find out the value of P. So now the drum is rotating in the counterclockwise direction. So this side of the belt will be the tight side having the tension T1. And this side of the belt will be the slack side having the tension T2. Now this is the free body diagram for the lever, which is having forces P, T1 and T2. So taking moments about the fulcrum point O, we have tension T1 will be rotating the lever in the anti-clockwise direction about the fulcrum. So the moment of tension T1 will be positive and the magnitude will be T1 into the distance A. The force P will be rotating the lever in the clockwise direction about the fulcrum. So the moment of force P will be negative and the magnitude moment of force P will be P into the distance L. Similarly, T2 will also rotate the lever in the clockwise direction about the fulcrum. So the moment of T2 will also be negative and the magnitude will be T2 into the distance B. So we can write the moment equation as follows: T1 into A, that is the positive moment, minus P into L and minus T2 into B will be equal to 0. From here we can get the equation of P as P is equal to T1A minus T2B divided by L. Now, as T1 is greater than T2, also A is greater than B, then this product of T1 into A will always be greater than T2 into B. So this P will always be positive. So under all conditions, the effectiveness of the brake will depend on this force P. Now let's see the other condition. That is, the drum is rotating in the clockwise direction. So when the drum is rotating in the clockwise direction, this side of the bend will be the tight side and having tension T1, and this side of the bend will be the slack side having tension T2. Now this is the free body diagram of the lever in this case, which is involving force P, T1 and T2. Now taking moments of the forces about the fulcrum O, we have T2 will rotate the lever in the anti-clockwise direction about the fulcrum. So the moment of T2 will be positive and the magnitude will be T2 into A, that is the perpendicular distance of line of action of T2 from fulcrum, that is nothing but A. Then force P will rotate the lever in the clockwise direction about the fulcrum. So the moment of force P will be negative and the magnitude will be P into the distance L. Similarly, T1 will also rotate the lever in the clockwise direction about the fulcrum. So the moment of T1 will also be negative and the magnitude will be T1 into B. So the moment equation can be written as T2 into A minus P into L minus T1 into B is equal to 0. T2 is the positive moment and P into L is the negative moment and T1 into B is the negative moment. So from here we can get the value of P as T2A minus T1B divided by L. Now as T2 is less than T1 and A is greater than B, so this brake will be effective as long as T2A is greater than T1B. That is, T2A should be greater than T1B. That is, T2 upon T1 should be greater than B upon A. So this brake will be effective as long as the ratio of T2 and T1 is greater than the ratio B upon A. Now suppose if T2A becomes less than or equal to T1B. So when T2 upon T1 becomes less than equal to B upon A, then P is 0 or negative. That is, the brake becomes self-locking as no force is needed to apply the brake. Once the brake has been engaged, no further force is required to stop the rotation of the drum. So when A is greater than B and force P is acting in the downward direction, if T2 upon T1 is less than equal to B upon A, then this configuration of the brake will be a self-locking brake. Fine. Now moving ahead to the second case, that is when B is greater than A or A is less than B. In this case, the force P has to be applied in the upward direction as shown here. So the force P is applied in the upward direction, then in that case this portion of the band will be lifted upwards and the band will be tightened and the brake will be applied. If the force is applied in the downward direction in this configuration, then the band will be loosened and the brake will not be applied. So let us first see the counterclockwise rotation of the drum in this case. So when the drum is rotating in the counterclockwise direction, then this side of the belt will be the tight side having tension T1 and this side of the belt will become slack side having tension T2. Now this will be the free body diagram of the lever having forces P, T1 and T2 again. Now taking moments about the fulcrum point O, we have T1 will be rotating the lever in the anti-clockwise direction. So it will have a positive moment with the magnitude of T1 into the perpendicular distance A. And P will also have an anti-clockwise rotation. So it will also have a positive moment with the magnitude P into L. But T2 will be rotating in the clockwise direction. So T2 will be having a negative moment with the magnitude T2 into P. So the moment equation can be written as T1 into A plus P into L minus T2 into B is equal to 0, where P and T1 are having positive moment and T2 is having a negative moment. So from here we can have the value of P as T2B minus T1A divided by L. Now here also, as T2 is less than T1 and B is greater than A. So this brake will be effective as long as T2B is greater than T1A or T2 by T1 is greater than A by B. So this brake will be effective as long as the ratio of T2 to T1 is greater than A by B. Now what will happen if T2B will become less than or equal to T1A? In that case, P will be either negative or 0. So the brake will be self-locking brake. So when T2 by T1 is less than equal to A by B, then P is 0 or negative. That is, the brake becomes self-locking as no force is needed to apply the brake. Once the brake has been engaged, no further force is required to stop the rotation of the drum. So in case of A is less than B and P is acting upwards, if T2 upon T1 will be less than or equal to A upon B, then this configuration of the brake will be self-locking brake. So moving ahead with the clockwise rotation of the drum. When the drum is rotating in the clockwise direction, so this side of the band will become the tight side and this side of the band will become the slack side. The tight side is having the tension T1 and slack side is having the tension T2. This will be the free body diagram of lever in this case, having forces again P, T1 and T2. Now taking moments about the fulcrum point O, we have T2 will rotate the lever in the anti-clockwise direction, so the moment will be positive and the magnitude will be T2 into A. Similarly, P will be also rotating the lever in the anti-clockwise direction, so the moment of P will also be positive with the magnitude P into L. But the moment of T1 will be negative as it will be rotating in the clockwise direction, and the magnitude of the moment of T1 will be T1 into B. So writing the moment equation, we have P into L plus T2 into A minus T1 into B will be equal to 0. So P and T2 are having positive moments and T1 is having the negative moment. So from here we can have P is equal to T1B minus T2A upon L. Now as T1 is greater than T2 and also B is greater than A or A is less than B, then under all conditions P will always be positive. So under all conditions the effectiveness of the brake will depend upon the force P. So these are the various cases of differential band brake, and depending on the value of A and B, you have the value of P, and accordingly the effectiveness of the brake is depending on the value of A and B and also on the direction of rotation of the drum and the direction of application of the force P. Now moving ahead, let's compare all these results. So when A is greater than B, so P should be acting downwards. For the counterclockwise rotation of the drum, this is the relation of the applied force, and for the clockwise rotation of the drum, this is the equation for the load applied. Similarly, when A is less than B and P should be acting up in the upward direction, so in the counterclockwise direction this is the relation, and for the clockwise direction this is the relation. The condition of self-locking in case of A is greater than B is T2 by T1 should be less than B upon A, and this will be obtained in the clockwise rotation. And the condition of self-locking in case of A is less than B is T2 by T1 is less than equal to A upon B, and this will be obtained in case of counterclockwise rotation as shown here. Having seen the condition of self-locking, we should understand where the self-locking is required. The advantage of self-locking is taken in hoists and conveyors where the motion is permissible only in one direction. If the motion gets reversed somehow, the self-locking is engaged, which can be released only by reversing the applied force. Now, having seen all these relations, we should now discuss about the effectiveness of the differential brake. The brake is said to be more effective when maximum braking force is applied with the least effort P. For the case 1, when A is greater than B and P is applied in the downward direction, the effort P required is less when the rotation is clockwise, assuming that the brake is effective. And similarly, for the case 2, when A is less than B and the force P is applied in the upward direction, the effort P required is less when the rotation is in the counterclockwise direction, assuming the brake is effective. So, in case of A is greater than B, clockwise rotation will be more effective, and in case of A is less than B, counterclockwise rotation will be more effective. Now it is seen in the above discussion that the differential band brake is more effective only in one direction of rotation of the drum. However, a two-way band brake can also be designed which is equally effective for both the direction of rotation of the drum. In such a brake, the two lever arms are made equal as shown here. So these two arms are made equal, and in all the conditions this configuration will be equally effective. So for both the rotations of the drum, the applied force will be T1 plus T2 into A by L. So this is all about the differential band brake. I hope you have understood the various configurations of the differential band brake and the equation of the applied force P, and also the conditions of self-locking in case of differential band brake. I also hope that you have understood the criteria for effectiveness of the differential brake. So this is all for today's lecture. In the next lecture, we will solve some numerical problems based on differential band brake. In case of any doubts, feel free to contact me. Thank you.